You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast, and I have Dr. Chris Barrett. He's Executive Director of the Biocomplexity Initiative, and he's a professor of computer science at University of Virginia. The Biocomplexity Institute was first started at Virginia Tech by him, and now has moved to the University of Virginia. So, Dr. Barrett, a.k.a. Chris, thanks for coming. How are you doing?
I'm doing well. Thank you very much for inviting me.
Yeah, so first, what is biocomplexity, and then what's the premise of your work?
Right. Well, in a nutshell, what we look at are what we call massively interacting systems. So they're systems built of really large numbers of interacting pieces that are heterogeneous. It characterizes not just all the cells in your body, but all the cellular machinery and all the signaling and all the stuff, and not just in your body, in ecologies, life on the planet, and even beyond that. I mean, we live in an environment that we create with our technology and interact with it. It co-evolves with us, and it arguably is a part of our living environment. So we take it as scientifically legitimate to look at these problems technically and in detail in the large and try to do practical things with them, ranging from epidemiology to the study of rethinking how bioinformatics can analyze patterns in nucleotide sequences to how public policy affects human health. And so we view these questions as all legitimate issues associated with the essential interaction of people and their infrastructure and their technologies, and we think they ought to be studied as a topic. So that's what it is.
So if these, the human body, I've heard in the literature, they say there's 10 to the 70,000 possible interactions just in the human body alone. But I mean, in looking at, people interacting with their environment and the ecology with each other, it just seems like these systems are unbelievably complex. How would you model them successfully, or how would you gain information from them?
Right. Well, that's sort of the question, and it's a really, really deep question. I don't know about that particular number. Let's just say they're astronomical numbers, but they're not. The thing is, there's structure. There's patterns and structure in these numbers and these forms. So at the foundations of this, we look at what are the mathematical and computational abstractions necessary for us to even represent these kinds of systems conceptually. What are the principles of them? And so, for example, the study of large dynamic networks as a mathematical object, a computational object, and also a theoretical sort of explanatory object is a major aspect of this. Its connections to theory of algorithms, as well as algebraic concepts and so on, statistical and probabilistic concepts. All of these things at the foundations allow us to be able to even frame what these questions are. But then if you stay only at that side of things, you sort of forget what you're studying. So so we take on actual questions. We don't try to answer every single question about the human body at once, or society or anything else, but we might be very interested in how flu epidemics operate and how to study them maybe a little differently than they've been studied in the past. And if we can get some insight into, on the one hand, individual biology, even individual choice behavior and activities, and the population level effects of a disease and how they affect things like public policy and pharmaceutical priorities and stuff. Those kinds of questions are the kinds of questions that we might take on that somebody cares about, and we tease them apart and we answer them in layers with the hope that eventually we'll kind of be able to stick all this stuff back together. But we do have, so we're not trying to answer every question at once. So my long-winded description of biocomplexity aside, that's what you say is true, but you pick it apart and you look at things that matter and you work on things that matter. So interdependent infrastructure, how that co-evolves with human activities, epidemiology, and how public policy interacts all the way down to, say, antimicrobial stresses on microbes that lead to antimicrobially resistant bacteria, for example, or how ideas spread in populations and lead to concepts of common knowledge. All those are fair. They have real applications, and that we work on them in terms of those applications and derive this theoretical program.
So, all right. So what are some of the main learnings that you've figured out from studying complex systems? It sounds like one thing you mentioned is, well, they always seem to have structure, so that helps simplify things. Are there any other overall themes that help you when you are trying to figure something out, like, again, how flu spreads throughout a population, or other examples?
Well, there are many, but the thing that excites me personally the most, this isn't necessarily true even for everybody on our teams, but me personally, what I think is interesting is how the deliberative behavior of individuals, not sort of en masse, but as individuals in interaction, can change things like epidemiological outcomes. I mean, if we have limited resources to deliver, say, antivirals in the face of a viral epidemic, and there's a question about whether we would sell them and let the market figure out the distribution of these things, or we would, in the name of the social good, calculate who needs to get them and deliver them into the world in some sort of fair and policy-driven way. Either one of those two options, we've studied this sort of continuum. What we find out is that the decision-making properties of individuals in these systems have a lot to do with, if you balance how you deliver these things and you allow people to be involved, things like their fear, how much information they have, how much money they have, what they're willing to spend, and their other constraints, all come together in ways that change how people behave and what they do, and that affects the outcome of diseases. So it isn't like we're just this, aggregate blob powerless against some virus. We're an active interacting system, and our individual sort of cognitive level behaviors, or if we add computers, computational features, actually are causal. They cause changes in this system. And that's a very, very compelling and interesting path into the future for a lot of reasons, not just about epidemiology. This is just an example, but it's a really, really cool thing that individual deliberation is actually, so important to things that don't seem to have anything to do with deliberation, like the spread of a virus in a population. That's interesting.
Well, all right. So I would figure that, yes, individuals can influence greater things in themselves, but I would also think in a lot of these systems you see kind of a Pareto or a skew or an 80-20, where maybe many individuals don't influence it much, but a few influence it in an outsized way. Do you see that, or do you see uniformity?
Well, Pareto, so things like Pareto, for example, or any other sort of like in epidemiology, there's compartmentalized models that take the whole population and divide them up into unexposed, exposed, susceptible, exposed, infected, and symptomatic people. And then there's these rate equations that drive things around into these pieces. You can treat things in these compartmented sort of aggregate models. You can do the same thing with Pareto sort of analysis at the level of markets, where people are just sort of blurred, or not just people, but agency, generally, companies and markets and all kinds of things are blurred into these these aggregates that have properties like Pareto. You can also take Pareto-like models or underlying generators that give rise to Pareto-like properties and assign them to individuals, and you have a whole different level of understanding about where things like those properties come from and how they apply and can be managed. So there's no question that there are aggregate level properties, composite sort of phenomenological characterizations of things, but there's also, and this is where the complexity part of this oftentimes comes from, it's not always true, but this bottom-up notion that most of complexity science in one way or another adopts is a really interesting thing to consider. And in living systems, of course, at the bottom, if you really start looking close, we're all just a bunch of little machines, interacting machines that don't know what they're doing other than their own little machine thing. Yet they give rise to these living systems, and I would just say that direction of work is also interesting, even with stuff like 80-20 Pareto and many other population level or aggregate level phenomena.
So what kind of systems have you studied in detail, and what interesting things jumped out at you from studying them?
Okay, well, we've studied lots of different kinds of systems. One of the jokes is when we start to give this presentation to in academia, say, well, this is sort of like the Department of Everything department, because we're really problem agnostic. We're really interested in these tools and methods. So the kind of
well, you got to have favorites. That's what I wanted to ask you.
Yeah. So we've done a lot of things. So starting back some time ago, we've looked at very large-scale warfighting systems, like campaign-level warfighting systems, armies in contact with armies, with air forces and navies and armies and all the things that constitute them in increasing level detail. This is just as a matter of to sort of go from our last point. There are also historical models in combat modeling that are based on aggregate models of attrition, which are also coupled rate equations. They're rooted in something called Lanchester equations, but they basically give you a population size and a rate of attrition. And so words like force multiplier and stuff like that have entered the vocabulary actually came from those old warfighting models. But those are also aggregate phenomena that we look at, like force multiplier is such a concept, just like Pareto. But there's in that sense, and but we look at these. We looked at these. This is some time ago in really a lot of detail, where individuals and individual units and so on were studied, so that if we change the technologies available to these individuals, if we empowered them with AI or different weapon systems or something, the outcomes would be different, or different communication systems, or even different strategies. And so this involved a lot of scale up to get to continent level or country level things with all these little bits and pieces. This was quite a while ago, but we also studied then the platforms themselves and AI being introduced in interaction with human, for example, air crew and fighter aircraft and stuff. Interacting satellites, small satellite systems, interacting space. So you can see that this is one sort of class of work that is network-centric and lots of pieces and has been studied in aggregate and needs to be known in detail, and it has all the properties I talked about. We studied those. We studied interdependent infrastructure, so socio-technical systems like transport, communication, energy systems, and them being coupled to one another. They don't exist without people, and they're driven by people's needs, and they exist not just at human scale, but they exist for human activities and have human health consequences and human behavioral consequences. In any case, we studied those for a long time. We studied transportation especially a long time, and focused on the detailed microsimulation of having every individual with an activity intention, with questions of behaviors and intermodal networks moving, and then calculating all the way up through traffic flows, and then measuring in, whether the traffic flows actually look like real traffic flows. And once we got it to where we could believe that, then we would change the world and say, what would happen. And you could couple that to air quality, and you can couple it to economics and a lot of other things. And we do similar things with electric power markets, where we looked at how electric power market dynamics are coupled to the control systems that operate the power generation and distribution systems. We're not the first ones to look at that, but we did look at that. And what we did do was take these disaggregate population activity models that were developed for things like transportation, adapted them, and used them for demand-side electricity models. And then that's another thing. Then we have looked for a long time now at infectious disease, social epidemiology. We generate the social networks that produce the interactions that the diseases, that produce the networks that the diseases spread in, depending on the kind of disease, the kind of interactions and stuff. This has a lot of influence on what you recommend to mitigate outbreaks. Things like understanding if you were in the middle of a pandemic or even a national epidemic, and you had National Guard forces that needed to be available to deploy, they needed to be combat ready, say, then the question is, what do you do? These National Guard guys are stuck in the civilian population like regular civilians. They're in the middle of an epidemic. How do you maintain force readiness for deployment? We've studied questions, many questions, but that was one of the questions we studied.
Well, you told me about a lot of the things you studied, but what about recommendations you've made, and did you observe the effects of them, and were there any surprises?
Right. Sure. Okay. Well, in every one of these systems, every one of these was built from the perspective of building analytic systems for decision making. None of them were built or taken into study for purposes of merely thinking about something, thinking about a combat system or thinking about a satellite system or about transportation. All of these were either in the acquisition process or in the specification and design process for these platforms. They were driven by these applications, and they affected these outcomes. In the case of the transportation systems, most of that work was funded by the Federal Transportation, the Department of Transportation, the Federal Department of Transportation. But they're deployed through the municipal planning offices. That's a long story, but that technology affected how plans that distribute this, trillions of dollars of infrastructure funding are used as relates to transportation planning. So every one of these has been used for the purposes of actual enabling decision analytics. In terms of the epidemiology work, one of our main sponsors, again, is the Department of Defense and the Threat Reduction Agency. Defense Threat Reduction Agency. We have a project there that's been going on for over 10 years. We develop a platform, and we work hand in glove with their analysts as questions arise and help them answer all kinds of questions about a variety of issues that come up. But some of them have to do, just continue what we were saying before, have to do with how epidemiological considerations affect unified commands in the field, and these questions come in real time to the technical reachback organization, and we work with them to do this. We also derive our research program to develop these tools in such a way that they actually support these real-world applications. And so it's a great question, and I'm really glad you asked it, because I don't know how I left that out, but we're driven by this. One of the most important aspects of this is we're talking about the extended capability of humans. This is in itself a biocomplexity issue to sense, perceive, interpret, and reason and act on the world that they live in in an increasingly networked world where the interactome that we are dealing with, and there's nothing virtual about this, is, for example, the computational and communications media layer. Those are real interactions. They're real human-mediated interactions, and they're transforming what human agency is. We don't really know very much about it, and we're building tools that fit in there anyway. So we're think it's a really interesting question that this is all rooted in application. 100% of it is rooted in application, and all of the research is being derived from needs that can't be met with, arguably can't be met adequately with existing less discrete and detailed analytics.
Well, do you feel like you've had enough sophistication to be able to model these complex systems, or have the attempts failed, or have they worked? Have they worked really successfully? What would you say?
Well, life is full of failure. But I would say that I can't think of any total failures we've had. We've had disappointments and partial failures here and there, I suppose, for any number of reasons. But generally speaking, I think the way that you would describe our overall progress is that we can do what we can do now. We're not going to lie to anybody about what we're able to pull off and what we're not. Our research will take us in a direction, and we get better and better and better over time. And I'll give you one example before I answer the other side of that question, like what are some successes? One example, this isn't one of those successes, but this is a good example. When we first started calculating like transportation systems, to calculate the person by person, second by second activity in an entire urban region with millions and millions of people in it would take, once we got everything set up, which might take 6 months, it would take like 3 weeks or something to run the calculations, to understand, to just run the calculation. A few years ago, 3 years ago or so, I guess, we have these tools had to work on that. That's not very useful. So our representations and our computational methods and stuff were all focused on scaling and exploitation of high performance computing to beat that problem, to beat problems like that, and to make it more available to other people. We use distributed computing techniques. And so we scaled up a few years ago to about 1 million processors, and we ran a 200-day epidemic in full detail with mitigation, completely non-scripted, individual by individual for the whole United States. And that 200-day epidemic ran in about 10 seconds. And so we're talking about a year's worth of work or 10 seconds over the last, is the progress we've made in terms of just realizability of these things over, say, the last 15 years or so. That's a significant, that's a very significant.
That's huge,
yeah. And now, in terms of what that buys you, we're now able to get inside real-world decision cycles where, with fielded units in certain kinds of environments, where you get a plan, the plan is agreed to and disseminated, people do whatever they do, more information comes in, you make another plan, and these work like in, say, 24-hour cycles. Let's say it doesn't have to be 24 hours, but let's say it's a 24-hour cycle. So, and let's say that you're on opposite sides of the world. So while it's daytime here and they're working, it's nighttime there, and things are playing out, and so on. So it could be, in West Africa, and the United States isn't quite 24 hours. Light dark, but it's different. So in the Ebola outbreak a few years ago in West Africa, we were involved in using these tools on first of all, just establishing what the dimensions and characteristics of the outbreak were, because the data was problematic to get. Knowledge of the area wasn't very good. The information was weak, and to understand how to stick together what we had and to be specific about what we needed, we helped in that process. To understand what the dimensions of the disease were, the disease had to be modeled, and it wasn't well modeled. We were able to pull that together pretty fast on this platform because it doesn't care what the disease is. You just have to get the parameters and stuff right. But we didn't know what they were, and even things like, where's the population, where are they going, and like, does the map say the roads are here, but if you see where the people are, they're not where the maps say the roads are. It's complicated. And then there were social determinants in their behaviors, like funerary practices and other kinds of sanitary practices and other things that were involved in the spread of this disease and were instrumental. And so, in addition, there was the supply chain logistical problem of the 101st Airborne Division delivering emergency treatment units into the, the United States is responsible for Liberia. So, you don't want to put a treatment unit in. It's like a tent hospital sort of thing. You don't want to put one of those things in someplace that suddenly pulls all these people together and creates a real hotspot for infecting people. On the other hand, you want it to be in a place where people will come. So you're going to use multiple of these things. You're going to put them in place where the next one goes is dependent on the reaction of the population to the first one and the progress of the disease. And so it's a very complicated nonlinear planning problem, and that was embedded then into all this other computational and projected machinery, and we did fit all that inside this 24-hour rotation cycle. So that's an example of where a research tool was used, technically speaking, for purposes of demonstration in an operating environment, and it was a bit of a success. And it used basically everything I told you about. It used infrastructure modeling, population modeling, mobility modeling, sort of onboard individual, sort of economic reasoning and behavior, health modeling, and many other, well, basically everything I talked about. And one of the things we also modeled was a communication system. So there's that. We've also modeled nuclear weapon detonations in Washington and all kinds of stuff for different people that have different uses. We're also doing scholarly work. I mean, there's for agencies that don't seem like funders of scholarly research necessarily, but if we get some bacteria in a sensor and we get some genetic kind of reasoning, date sensing, we get some PCA stuff out of some of these samples, and we want to know, is this a threat? Does this look like something that would be potentially virulent? Turns out virulence is a really hard thing to understand genetically. In fact, virulence is just a really hard thing to understand. And we have a project where we're teamed with other researchers at other universities that are specialists in synthetic biology and other kinds of areas, and we're doing genomic modeling and things to try and get a handle on how to estimate virulence from samples, from these sort of samples, genetic samples from sampled, say, microbial environments. We run a microbial database for the NIH. The University of Chicago is the lead on this now, but we've been doing this now for 15 years. It's a very large project. It's one of 3, they're called BRCs. I'm not sure it must be biological research centers, but I'm not positive if it means that. But it's called Patrick, and it's a microbial data library for all of the microbial genomic information from all the researchers that do microbial research in the NIH. There's over 200,000 microbes that are genomically and many of them metabolomically characterized in this data library, and there's tools to analyze them and study them and stuff, and many other things like that. So there are scholarly activities, but the driver for this comes out of doing stuff. Like, we need to expand people's capabilities to deal with this extremely complicated world, and they have to do that. And we should be serious about taking the real problems they have to deal with and extending their capabilities to deal with them, not break it into little pieces that don't fit together very well.
What do you know about complex systems that you didn't used to know, and maybe how have your beliefs changed or your thoughts about complex systems changed recently?
I was around at sort of just at the end of the first generation of the Sanitary Institute, which is sort of one of the mecca points for, well, I shouldn't say that, one of the original locations for the serious consideration of complexity science and complex systems. I retired from Los Alamos before I went to the Virginia Tech, and I was there a long time. And at the beginning of the time I was there, was still in the early stages of establishing the respectability and the reality of this kind of thing being a discipline. And at that time, it was heavily influenced and driven by physicists. And not too surprisingly, and given its proximity to Los Alamos and the connections to the other folks that were associated with the startup of this, but also economics and other things. So there, Kenneth Arrow was there, and on the economic side of things, and Marie Gilman was there. There's plenty of physics side of things. So there's lots of tension, but it was all these sort of traditional disciplinary sort of silos, wondering if maybe physics could be extended to to consider complex systems, or whether economics held the key and game theory or something held the key to understanding what we meant by complexity, and it was focused on a analytical and a mathematical perspective that was very much rooted in where those disciplines came from, and it was really exciting and beautiful, and still is. But it's evolving to now and so the physicists were running around telling everybody how they were going to do biology, or whatever. Economists were telling people what evolution really meant, and so on. So now what we begin to see is that computer scientists are doing that. now that computer scientists are taking over, psychology, they're taking over biology, and this is a very, very interesting situation. It almost certainly is a new phase, but this is a fundamentally different and interesting phase. And so I think I would say that what I believed it at the beginning, but what I believe more and more is that there really is something to this notion of complexity science, or complexity, this idea of the importance of local properties as well as emergent and co-evolving global constraints that are structural. They could be structural in the dynamics. They could be structural, in static features. They could be structural in the form of social rules and common knowledge. Things like laws are structures that frame domains of decision making that individuals can engage in, and rules of interaction, and those rules of interaction and those boundaries constrain or define even social structures, which is their purpose, I guess. I think we have a much richer understanding of that. And what I think the most surprising thing to me is that I think we're coming up on a place where we can really say that instead of what I was talking about before, we want to extend human sensing and perception and reasoning and stuff. I actually think that what we're coming to is that cognition itself, mental processes that are decentralized, that don't live inside any particular, say, person, are really important. That organizational structures think it by every reasonable definition of what that might mean, have a mental characterization that is causal. It's not just some funny thing to talk about, like Timothy Leary might want to talk about. Not like that. Like it has engineering and economic and social and consequences. And that and this is really becoming more apparent to me. And I'm very surprised. I mean, to the point that I wonder if any reasonable definition of cognition requires that the thing that's cognate, or mental constructs generally maybe, that the cognate thing has to be alive even. It's not. I'm not sure that life is a prerequisite for mental properties. I mean, it just seems
earlier you seemed to say though that we're humans, for instance, are just a bunch of dumb machines. Maybe I mischaracterized what you said, but now you're extending cognition to non-living things.
Yeah, well, I mean, we are of course made of the same kind of, we're made of stardust, right? And so that's just the truth, and configurations that spontaneously come together these are autocatalytic forms. So they form themselves, they create themselves, and they elaborate themselves. And I'm saying that there's this other kind, this mental kind, this sensing, interpreting, deliberating, supervening.
You think that's a property of a complex system itself?
Yes, I think not only do I think that, I think it looks more and more like that's a completely legitimate way to. There's certain constructions when you get certain kinds of instructions, then you have something to see. Otherwise, frankly, we wouldn't be able to make any kind of something or other out on a computer that we could legitimately call machine learning, for example, or machine like visual identification or something. These are they're not alive yet. I mean, they're not like they don't, but those are proto-cognitive or proto-mental features, and we're right on the edge of these things where we look at organizations themselves, like organizations of machines and people, or even just people, organizations of people, that the organization itself has what, by any reasonable definition, looks like cognitive properties. It learns and adapts and remembers and is robust to replacement of individual parts and all of those kinds of things. Those kinds of features just, so we don't know what I'm talking about. We don't know how to think about that yet. But what I'm surprised by is that I think this is appearing on the not very distant horizon, that we are going to have to deal with this directly. This is not going to be, like I said, some sort of purely intellectual conversation. This has meaning, and I'll give you an example of where it can have meaning. A really important example is that there's almost a canon in science that wherever the truth might mean, we're not sure exactly what it means, but whatever it is, data is the source of the truth. And I think that we have to realize that in things like military systems, financial systems, and just everywhere, viruses interacting with cells and frogs that are camouflaged and every other thing you can imagine, deception and the untrustworthiness of basic data is a natural form. First of all, this implies that interacting cognitive systems are driving basic evolutionary processes, because you wouldn't be camouflaged if it didn't work. To be camouflaged, some aspect of the system has to recognize that whatever's looking at it thinks that's a leaf. Now, it doesn't have to do it in a way that I just said it, and it can be all bottom up and everything, but that has been hit on. There's a representation, and it leads to actions that are beneficial to one thing at the cost of another thing. These are deceptions. In rethinking interacting cognitive systems, this naturally occurs. It occurs in a deliberative system where you have causal things that are associated with, by state interpretation and deliberation. These issues come up. So what I'm saying is, with these systems,
do you think in non-living complex systems that cognition is an emergent property of the system, or is that way off base?
What I was saying a little earlier is, I think that in non-living cognitive, if you have protocognitive pieces and they can be set into the right configuration, then I would think that you would probably get something that by any estimation would have to be considered cognitive. And it wouldn't have to necessarily be living. And what I'm furthermore suggesting is, as an example, and certainly not the only example, but in this extension of human activity where we have moved agency, like the thing that pays your bills, the thing that covers your debt with your money, not being it's being an agent that's assigned by somebody or something, ultimately by you, that lives in cyberspace, that executes your will. You're surrounded by sub-agents that are as connected to you as your own arms and fingers from the point of view of personal agentic responsibility. And those things do things. And the sophistication of those agents and their networks are growing. And what I'm saying is that humans in that interaction, the human connection to that medium of interaction, is something that will transform concepts of agency, responsibility, who you are, the definition of what it means to be a person. And I think it's happening very quickly. And what I'm moreover saying is, in there, issues like deception, this is just Dodge City in there right now. We don't really understand it. It's just running. And it's very interesting that we are having, so we implement things like social media. Everybody likes social media. Everybody uses it. At the same time, everybody is aware that things like Arab Spring and the sequelae from Arab Spring, and in the current political climate, our politicians, our national leadership is communicating and affecting individual behaviors and beliefs with stuff like social media, and not through conventional media. When the Constitution was written, the post office is in the Constitution. It's democracy is the technology for distributed decision making and the distributed sovereign. The post office is the communication system. It's a technology, and it's enshrined in the Constitution. And we have the communication platform that we have now goes far beyond the traditional post office, but it's still associated with the distributed, agency of things like the distributed sovereign. And so I'm just telling you that it's clear that we have social disruption and even phrases like fake news and stuff flying around that tell us that the use of information in these complex interactions is really pertinent, incredibly pertinent, and we don't understand the cognitive environment that we're in, and we don't understand its composed social effects. The fact that that is so important and real, all of a sudden, right now, when I launched on this, all I meant to say was, that's very surprising to me. It's very surprising that we are at the place where we have to take this seriously, and it's not something we can think about at some institute, but it really doesn't change anything in the real life, which brings me back to your question. Do you really ever change anything? Do you really ever, do anything real, or you just sit around worrying about like all these interacting things? Well, this is my answer. We have to this is real. and having an environment or even a point of view with respect to it, I think is reasonable and important. And so we'll work on these more sort of daily practical issues, but I'm very surprised that we're technologically and scientifically at this state, both in terms of our ability to build things and our inability to understand what they're doing. And I think they're essentially cognitive, and they need to be understood in computational terms. And that's really, I think it's super exciting, but it's also, it's important that this be dealt with because the consequences are real. These are not simple things, in my opinion. So anyway, it's pretty surprising thing. I think it's really exciting, and that's where I am.
Well, very good. We're about out of time, and I guess if this were a simple conversation, it would be ironic, given that you deal with complexity all the time. So what's the best way for folks to learn more about your work and to learn about biocomplexity in general?
Well, we've just moved to the University of Virginia, and we have not completely gotten our website back up, but we do have a Biocomplexity website at the University of Virginia that's easily searchable, and you can find it and click onto it. It'll help, and on there, the most important thing is you can find some names and some email addresses and some lists of publications. The other thing I would suggest, just from the point of view of any kind of rationale for the last thing I was talking about, is there's a book, it's become actually very popular. I'm sort of surprised about that too, but it's called Supersizing the Mind. It's by Andy Clark. It's kind of a strange name for a book, in my opinion, but it's an incredibly good book. Andy Clark is a philosopher of science and cognition, I guess, of mind. It's in the United Kingdom. He is. That's a really, really fine book. It's a little bit old now, but he wrote the original paper with a man named David Chalmers at ANU, at Australian National University. It isn't about what I just talked about, but it opens your mind to thinking about the distributed mind in a way that I think is really helpful. And there's just, once you go down that path, you'll see a lot of things. In fact, there's a wonderful old book. I don't know if people want to read old books or not, but it's a science fiction book. It's by E.M. Forster. I think it's from the early 1900s, but it's called The Machine Stops. And it's an environment that people interact only through video teleconferencing in little rooms, and they don't come in contact with one another in a honeycomb underground. And it's doesn't end well. But it's amazing how we foresaw where we are. Yeah. Yeah.
Well, very good. Well, Chris, I appreciate you coming on and talking about issues that, very few people contemplate at all. So thank you for coming on the podcast.
Well, thanks for inviting me.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.